purpose of this video is to go over some questions from Chapter 4 and Chapter 5 in the homework. This first question we're going to look at, we're given the second derivative of the function, right? And we're asked to find the original function given these two initial conditions. So when we integrate a second derivative of a function with respect to x, that's going to give us the derivative of the function plus some constant c. We're going to use the fact that we know if we plug in pi to the derivative of the function, we should get 7. That's going to be used to calculate the c value. And then we're going to do the same thing for when we integrate this should be derivative. When we integrate the derivative, we get the original function, plug in the value of pi to solve for that corresponding constant. And that's going to give us the function that satisfies the initial conditions as well as the derivative being cosine. So let's see if we integrate cosine of x with respect to x. That's giving me sine of x plus c. This is going to be f prime of x. Well, f prime of x at pi, right, f prime at pi is going to be 7. So what is sine of pi plus c? And sine of pi is 0 plus c equals 7. So that tells me that f prime of x is going to be sine of x plus 7. That satisfies the initial condition there. So if I do this one more time, if I integrate sine of x plus 7 with respect to x, so the integral of sine of x with respect to x would be minus cosine of x plus 7x plus a constant. So now this is going to be f of x, but I'm going to use the last initial condition where if I plug in f of pi, I'm going to get 9. So that gives me cosine of pi, which is minus 1, but I have a negative here, so I'm going to write minus 1 plus 7 pi plus c. And I want that to equal 9. So I'm going to have to drop down here. I would have 1 plus 7 pi plus c equals 9. So subtract 1, subtract 1, subtract 7 pi, subtract 7 pi. And that gives me c equals 8 minus 7 pi. So then my function f of x is going to be minus cosine plus 7 pi plus 8 minus 7 pi. So simplifying, minus cosine of x plus 8. And you can check yourself by plugging in pi. So if I plug in pi here, I would have minus 1, so that'd be positive 1 plus 8, which is 9. If I take the derivative, then I would have sine. And if I plug in sine, I would have the derivative of cosine is going to be minus sine, but the negative, so it gives me positive sine. If I plug in pi, should I get 7? So something happened there. I did not get 7. What do I need to evaluate here? This is 9. 9 minus 1 is 8. I have 7 pi. Subtract 7 pi. I get minus 7 pi. And that's c. Oh no. Oh, I still have this 7x here. That's my problem. That's not 7 pi, that's 7x. Okay, so sorry for that. This would be plus 7x plus 8 minus 7 pi. There we go. There's my equation. So the functions here, this c would then be 8 minus 7 pi. That's 7x. Okay. So you should be able to kind of check yourself there and see going about it. And you can see if you take the derivative, the 7's still there. But if you take the derivative a second time, it goes away and you get that positive cosine of x. Here, use the sigma notation. So if you recall, the function k goes from 1 to n of f of xk star, depending on if it's a right hand, left hand, or midpoint, times this delta x. So f of xk star also has the delta x in there. So if you recall, xk star equals a plus k delta x. And the delta x was calculated as, in this case, 3 over 20, right? So if we plug in a would be 0. So if I plug 0 plus k times 3 over 20, this x k star would be 3 over 20k. That is what I plug into my function here. So I have the sigma k goes from 1 to 40 of f of xk star is 3 over 20k, so this would be 3 over 20k plus 10, and all that is multiplied by delta x, which is then 3 over 20 again. And that's why you have the 3 over 20 in there, like so. And then calculating it, you can use the formula. You can plug in, you can use your calculator. It should be able to calculate out. So once you have xk star, you plug xk star back into the original function, and then you still need to multiply that by delta x. This next example is starting with the idea of what the integral means, and the integral means the area underneath the curve. And so if I'm looking at the area from -2 to -2, in this case, so if I'm integrating from -2 to -2, that integral is 0 because you don't have any width, right? So with what we're kind of doing here is we're breaking this up into rectangles, and the delta x is your width. If you don't have a width, then you don't have an area. So f at 8, so here we're looking at this one, so f at 8 would be the integral from 4 to 8 of f of t with respect to t. So looking at this function, I'm integrating from 4 to 8, and that area would be 9, which is given from the graph, but it's below the x-axis. So you have to be careful if you're looking for f of x or you're looking for a of x. A of x is an area, and it's always going to be positive. F of x is going to be the value of the function, well, in the area, and it can be positive or negative. Sorry, I misspoke. They're both saying the same thing. Area from -2 to x or from 4 to x. So it could both be negative. I'll also put a link to the video that's online for this. It does a pretty good job explaining it. So here, f of 8 means I'm using this one. F of 8 goes from 4 to 8 of this function. So I'm looking at this area, which would be -9. And then a of 4 would be the integral from -2 to 4 of f of t dt, which would be -2 to 4, which is going to be the integral from -2 to 0 of f of t dt plus the integral from 0 to 4 of f of t dt, because that's what's given. This area here is 9 plus this area here is 16. So 16 plus 9 would be 25. So that area is 25. If we look at f of 4, then we're taking the integral from 4 to 4 of f of t dt, and that is 0 because I don't have a width there. And then a of 8 is going to be the integral from -2 to 8 of f of t dt, and that's going to be the whole thing here. Keep in mind, if it's above the x-axis, it's positive. If it's below it, it's negative. So it'd be +9 plus 16 minus 9, which give me 16. So minus 2 to 0, 0 to 4, and 4 to 8 would be encompassing all that. So hopefully that helps on this one. Pretty straightforward on the area underneath the curve from A to B, depending on the notation. In 5.3, 20 and 21, this is really playing the benefit to calculus here. These are inverses of each other. If I said A plus B and then minus B, that's going to be A. Or A times B then divided by B, that's A. These are inverses of each other. They can cancel each other out, and you get what you originally started with. The derivative is the inverse of the integral. So if I integrate this with respect to t, I'm going to have a function of t, but then I'm going to plug in two values, and then I'm going to differentiate it a function of x. So whatever this is here, this antiderivative, call it big F, right? Big F at 4 minus big F at x, right? Then if I was to differentiate this, differentiate with respect to x, this is a constant, so that's 0, minus, this would be little f, because the antiderivative is big F, so the derivative is little f at x. So what this means is I take this function inside here, and I replace, everywhere I have a t, I replace it with x, and then I have that negative out front. So it ends up being negative square root of x cubed plus 3. We can do the same thing over here, right? I'm integrating this, so I'm going to call this big F. I'm going to plug in x squared minus big F at 0. Then if I take the derivative with respect to x, I have a chain rule here. So I have the derivative of the outside, which would be little f, evaluated at the inside, times 2x, minus the derivative of a constant, which is 0. So what this is saying is this is the original function, right? Everywhere I have a t, the original function in this case, I'm going to rewrite it here, f of t is 1 over t squared plus 18, right? Because the dt comes out front. So I'm going to replace that. Everywhere I have a t, I replace it with x squared. So I have 1 over x to the 4th plus 18, and then this is that chain rule times the 2x, which gives me this expression here. So you don't actually have to calculate the integral, plug in the upper bound and the lower bound, and then take the derivative. You can do it using a shortcut of saying, I don't know what the integral is, but it's just going to then take the derivative of it, so I'm just going to call it big F, plug in the upper bound minus the lower bound, and then take the derivative. Here I have to use the chain rule. I take the derivative of the big function, which is f of x, so evaluated the inside, times the derivative of the inside with respect to x. So hopefully that kind of helps those click there. This equation, this is the last one on the homework, 5.3 through 5.9, I believe. And what you're doing here is you're setting this up with doing a u substitution and making the problem easier to solve. So here's the u substitution here. So that changes the bounds. If I plug in p equals 1, then u would be 0. If p is e squared, then u is 2. So I can change the bound here, integrating from 0 to 2 of u divided by p, and then here I can, dp would be p times du, which would cancel out the p in the denominator. So I'm left with this relatively easy integral, and then I plug that in and I get my answer as 2. So kind of seeing that if you have, an ln of p, you want to simplify that, so you just have u as ln of p, then du is 1 over p dp. That simplifies it to integrating u, which is very easy and straightforward. Plug in the bounds in terms of u, upper bound and the lower bound in terms of u, and then you get your answer. So hopefully this video helped kind of summarize any of the questions you had. If you have any other questions on the homework, please let me know and I can create another video, or we can meet up a time to go over these online.